On the morning of March 7, 1943, inside the sprawling Chrysler tank arsenal in Warren, Michigan, production supervisor Harold Brennan stood before assembly line number 4 with his clipboard, watching welders secure armor plates to tank hulls with the methodical precision that had defined American military manufacturing for 2 years. The air tasted of metal shavings and welding smoke, and the thunderous rhythm of hydraulic presses shook the concrete floor every 8 seconds. Brennan believed, as did every engineer and manager in the facility, that they had perfected the science of tank production, that every motion had been studied, every second accounted for, and that the current output of 23 medium tanks per day represented the absolute ceiling of what human ingenuity could achieve. He had no idea that within 6 hours, a third-shift riveter with a 7th-grade education would prove every assumption wrong and transform American armor production forever. Before we dive into this story, make sure to subscribe to the channel and tell me in the comments where you're watching from. It really helps support the channel. What happened that day would reveal how institutional thinking, no matter how sophisticated, could be shattered by someone who simply refused to accept that the impossible was truly impossible, and how a single act of defiance against established procedure would cascade into a production revolution that military planners in Washington had insisted could not occur before 1945. The Chrysler tank arsenal sprawled across 113 acres of former farmland, a cathedral of industrial might that had risen from empty fields in barely 18 months. Inside Bay 7, where medium tank M4A1 hulls took shape, the assembly process followed a rigid sequence that engineering teams from Detroit's automotive elite had designed with mathematical precision. Each tank required 1,673 individual operations, performed by workers who had been farmers, shopkeepers, and housewives before the conflict transformed them into precision manufacturers. Thomas McKinley, the plant's chief production engineer, had spent 11 months refining the workflow, studying motion and time with the intensity of a watchmaker examining gears. His team had determined that the optimal production cycle for a single tank hull required 47 hours and 12 minutes from the moment raw armor plate entered the line until the completed hull rolled toward final assembly. They had calculated tolerances down to the millimeter, scheduled worker rotations to prevent fatigue errors, and created a system that flowed with the elegant inevitability of a mathematical proof. The numbers backed their confidence. In February 1943, Chrysler Tank Arsenal had delivered 689 completed tanks to the Army Ground Forces, maintaining quality standards that exceeded specifications. Rejection rates had dropped to 1.3%, and production costs per unit had fallen by 18% since the previous summer. The facility operated 24 hours daily, across 3 shifts, employed 11,200 workers, and consumed enough electricity each week to power a city of 50,000 people. But on line 4 during the day shift, a problem had emerged that threatened to disrupt the entire schedule. A shipment of armor plate from the Bethlehem steel mill in Pennsylvania had arrived with dimensions that varied by 3/16 of an inch from specifications, small enough to pass initial inspection, but large enough to create alignment problems during hull assembly. The variance meant that workers had to manually adjust each plate before welding, adding between 8 and 12 minutes to every operation that touched those plates. Harold Brennan had reported the issue at the morning production meeting, where McKinley and the other supervisors calculated the impact. With 470 plates from the defective shipment already in the production queue, they faced a potential delay of 63 hours across the entire line. McKinley had authorized overtime and reassigned workers from other sections to absorb the disruption, accepting the reality that some problems could only be solved through additional labor and time. The decision reflected the prevailing wisdom of American industrial production, a philosophy that had built the most powerful manufacturing economy in human history. When faced with obstacles, you applied more resources, more workers, more hours, more precision. You studied the problem, broke it into components, and solved each piece through systematic application of engineering principles. It was the method that had built the Empire State Building in 13 months, launched Liberty ships in 45 days, and turned automobile factories into arsenals that supplied a global conflict. What no one in management considered was that someone might simply ignore the problem entirely and do something completely different. Walter Kowalski had worked at Chrysler Tank Arsenal for 14 months, assigned to third shift in Bay 7 as a hull riveter. At 42 years old, he had spent most of his adult life in automotive factories, learning manufacturing through experience rather than textbooks. Before the conflict, he had worked at the Dodge main plant, where he had operated everything from stamping presses to final assembly stations. He could read blueprints, understood tolerances, and possessed the kind of intuitive mechanical knowledge that comes from decades of working with metal and machines. He also had a reputation for doing things his own way, a characteristic that had nearly gotten him transferred twice in his first year. Supervisors noted that Kowalski frequently modified his work procedures, often completing tasks in sequences that deviated from the official process sheets. When questioned, he would shrug and explain that his method worked faster or produced better results, demonstrations that usually proved him correct, but also frustrated managers who valued adherence to established protocols. On the evening of March 7th, Kowalski arrived for third shift at 10 o'clock and immediately noticed the commotion around Line 4. Day shift workers were explaining the armor plate problem to their third shift replacements, describing the tedious process of measuring, adjusting, and rechecking each plate before welding. The mood was resigned, the kind of collective frustration that settles over workers facing hours of repetitive, annoying work that couldn't be avoided. Kowalski listened to the explanation from day shift riveter Bill Henderson, who demonstrated the measuring and adjustment procedure with evident irritation. Henderson explained that engineering had determined this was the only acceptable method to maintain hull integrity, that any attempt to force the plates without adjustment would create stress points that could compromise armor protection. He showed Kowalski the deviation measurements, the adjustment specifications, and the verification checklist that had to be completed for each plate. Then Henderson went home, and Kowalski stood looking at the stack of problem plates with an expression that his co-workers had learned to recognize. It was the look he got before he decided to try something that would either work brilliantly or get him called into the supervisor's office. What Kowalski understood from pure experience rather than engineering theory was that metal was not as rigid as the specifications suggested. He had spent years watching how armor plate responded to heat, pressure, and stress, observing behaviors that weren't always captured in technical manuals. He knew that the tolerance specifications built in safety margins, that the engineers in their calculation had assumed worst-case scenarios, and that in practice, metal often behaved with more flexibility than the numbers indicated. He also knew something else, something that came from 14 months of repetitive work on identical hulls. The welding process itself generated enormous heat that caused metal to expand and then contract as it cooled. The official procedure called for precise plate alignment before welding, but Kowalski had observed that the thermal dynamics of welding often shifted plates slightly anyway, meaning that some of the precise pre-alignment was wasted effort. Standing at his riveting station, Kowalski made a decision that violated every protocol in the production manual. He picked up one of the problem plates, skipped the entire measurement and adjustment procedure, and simply fitted it directly to the hull, using his experienced eye for alignment. Then he began welding, working with the rapid confidence of someone who had performed this operation thousands of times. The plate seated properly, the welds held perfectly. The hull integrity remained intact. Kowalski completed the operation in 6 minutes, compared to the 16 to 18 minutes the official procedure required. He had just saved 10 to 12 minutes per plate through the simple act of ignoring the problem that everyone else was carefully solving. He looked at the remaining problem plates, did some quick mental arithmetic, and realized what he had discovered. If his shortcut worked consistently, he could process these supposedly defective plates faster than normal plates using the standard procedure. The flaw that was slowing down the entire production line could actually be irrelevant. For the next hour, Kowalski continued working, testing his theory across multiple plates. Each time the result was identical. The plates fit, the welds held, The hulls met specifications. He varied his approach slightly, experimenting with different fitment techniques, but the outcome remained consistent. The careful measurement and adjustment procedure that engineering had mandated was solving a problem that didn't actually need solving, at least not in the way they had determined. By midnight, Kowalski had processed 32 problem plates, completing them at a pace that exceeded even normal production speeds. Other workers on Line 4 began noticing, at first with skepticism, then with growing interest. Frank Kowalski, a hull assembler at the next station, who was no relation despite the shared surname, stopped by to watch Walter work. Frank Kowalski observed the process for 15 minutes before speaking. He said Walter was going to get himself in trouble if a supervisor caught him skipping the adjustment procedure. That engineering had mandated that process for good reason. That quality control would reject any hulls that hadn't followed proper protocols. Walter Kowalski didn't look up from his welding. He said the hulls would pass inspection because they were perfect, that the adjustment procedure was solving a problem that didn't exist, that sometimes engineers overthought things because they were calculating for theoretical worst cases instead of actual working conditions. Frank remained skeptical, but he also couldn't argue with the results he was watching. The welds looked flawless, the plate alignment was precise, and the work was happening at remarkable speed. He asked how Walter knew the plates would hold under field conditions, how he could be certain that skipping the adjustment wouldn't create structural weaknesses that might appear only under stress. Walter set down his welding torch and looked at Frank directly. He said he had been working with armor plates since before either of them knew there would be a conflict, that he understood how metal behaved under stress better than any engineer with a slide rule, that the specifications were conservative because they had to account for workers who didn't have experience, but that someone who knew what they were doing could read the metal and understand what it needed. It was the confidence of craft knowledge confronting theoretical knowledge, the eternal tension between those who work with their hands and those who work with calculations. Walter wasn't dismissing engineering. He was arguing that engineering created rules for general application that didn't always account for the judgment of skilled practitioners. He believed, based on 14 months of repetitive experience, that he could see things the specifications couldn't capture. Frank thought about this, then made a suggestion. He said that if Walter was right, if this shortcut really worked, then someone needed to tell management, because the entire production line was being slowed by a problem that apparently didn't exist, and if Walter's method could be proven and scaled, it might change everything. Walter looked uncomfortable with this suggestion. He said management didn't listen to line workers about production methods, that they trusted their engineers and their procedures, that suggesting their carefully calculated process was wrong would be seen as insubordination rather than innovation. He said he was just trying to do his job efficiently and didn't want to cause trouble. But Frank persisted. He pointed out that the facility was under enormous pressure to increase production, that military planners needed more tanks faster, that if Walter had discovered a genuine improvement, keeping it secret was actually working against the larger mission. He suggested they at least document what Walter was doing and present it to their shift supervisor with actual results, rather than just theory. Walter considered this, then reluctantly agreed. He said they would finish the shift, process as many problem plates as possible using his method, and document the time savings and quality results. Then they would present it to supervision and let management decide whether to pursue it further. He made Frank promise not to exaggerate or oversell the discovery, saying he wanted the results to speak for themselves, without hype or drama. For the remainder of third shift, Frank became Walter's unofficial assistant and documentarian, recording operation times, counting completed plates, and noting quality observations. By 6 o'clock in the morning, when day shift began arriving, Walter had processed 168 problem plates that would have taken the day shift approximately 47 hours to complete using the official procedure. Walter's actual time, including brief breaks, was 11 hours and 40 minutes. He had worked 4 times faster than the engineering estimate by doing something management would have considered impossibly risky or simply wrong. The morning shift change brought Harold Brennan back to Line 4, where he immediately noticed something peculiar. The stack of problem plates that should have grown overnight had instead diminished substantially. He checked his production logs, confirmed that third shift had been scheduled to work on those plates, and tried to calculate how they could have processed so many in a single shift. The math didn't work. According to his calculations, third shift should have completed approximately 35 to 40 plates using the approved adjustment procedure. Instead, his count showed 168 plates processed and already integrated into hull assemblies moving down the line. Brennan felt a spike of alarm. The only explanation was that third shift had skipped the adjustment procedure entirely, which meant those hulls might be structurally compromised, which meant they might have a quality control crisis that could result in rejected tanks and a complete production stoppage while every hull was re-inspected. He immediately paged the quality control supervisor and requested emergency inspection of all hulls completed during third shift. Then he went looking for whoever had been working at the riveting station, determined to find out what had happened and why established procedures had been violated. Frank Kowalski, who had stayed past his shift specifically to explain the situation, intercepted Brennan before the supervisor could build up more alarm. Frank explained calmly that they hadn't skipped procedure carelessly, that Walter Kowalski had discovered the adjustment process was unnecessary, that all the plates had been fitted and welded to perfect specifications, and that they had documentation of the entire process, including time measurements and quality observations. Brennan's initial reaction was exactly what Walter had predicted. He said that line workers didn't have authority to modify engineering procedures, that the adjustment protocol existed for documented technical reasons, that skipping it constituted a serious violation that could result in disciplinary action. He said that experience didn't override engineering calculations. That feeling confident about metal behavior wasn't the same as knowing structural tolerances, and that if those hulls failed inspection, the responsibility would fall on everyone involved. Frank let him finish, then simply suggested they wait for the quality control results before making any decisions about discipline or procedure. He said the hulls would pass inspection perfectly, that Walter's work was flawless, and that if Brennan looked at the documentation, he would see that something remarkable had happened. The quality control inspection took 3 hours. Inspectors measured every dimension, checked every weld, tested structural integrity, using standardized procedures that included stress testing and visual examination. They compared the third shift hulls against specification requirements and against hulls produced using the official adjustment procedure. At 11:15 that morning, Quality Control Supervisor Richard Chen delivered his report to the production management meeting. Every hull from third shift met or exceeded specifications. Weld integrity was perfect. Structural tolerances were within acceptable ranges. There were 0 defects, 0 deviations, and 0 reasons for rejection. In fact, Chen noted with evident puzzlement, the third shift hulls showed slightly better dimensional consistency than hulls produced with the adjustment procedure, though he couldn't explain why. The room went silent as the implications settled. Someone had discovered that an engineering procedure, carefully calculated and formally mandated, was not only unnecessary, but actually counterproductive, and that someone was a line worker with no formal engineering training who had made his discovery through practical experience and intuitive understanding of materials. Thomas McKinley, the chief production engineer, asked to see the third shift worker immediately. His tone suggested he wasn't certain whether to be angry or intrigued, whether this represented a dangerous breach of protocol or a potential breakthrough. He wanted to understand exactly what had happened and why it had worked. Walter Kowalski was located at his home where he had gone to sleep after his shift. He was called back to the plant, arriving around 1 o'clock in the afternoon with obvious reluctance. He had not wanted attention, had not sought recognition, and appeared distinctly uncomfortable as he was led into a conference room filled with engineers, supervisors, and production managers. McKinley asked Walter to explain step by step what he had done and why. Walter, speaking slowly and choosing his words carefully, described his observation that the adjustment procedure was solving a theoretical problem rather than a practical one, that the thermal dynamics of welding made precise pre-alignment partially irrelevant, and that experienced workers could achieve proper fitment through visual assessment and tactile feedback, that was actually more reliable than measurement-based adjustment. He acknowledged that his method required skill and experience, that it wouldn't work for inexperienced workers, and that engineering specifications were appropriate for general procedures. But he argued that the facility employed hundreds of skilled workers who could perform at higher levels if given the flexibility to apply their craft knowledge, and that the current system was designed for the lowest common denominator rather than leveraging the capabilities of the best workers. McKinley listened without interruption, his expression unreadable. When Walter finished, McKinley asked if Walter believed his method could be taught to other experienced workers, if it could be standardized in some form, or if it was purely intuitive and therefore impossible to replicate systematically. Walter thought about this, then said it could probably be taught to workers with sufficient experience in metal fabrication, that it required understanding how different metals responded to heat and stress, and that someone with a few years of welding or riveting experience could learn it. He said it wasn't magic or mysterious. It was just applied knowledge that came from doing the work rather than calculating about the work. This answer clearly interested McKinley. He asked Walter if he would be willing to work with engineering to document his method, to help identify which aspects could be formalized and which required judgment, and to potentially train other workers if the approach proved scalable. He said that if Walter's technique could be safely extended across the production line, it might significantly accelerate output without compromising quality. Walter agreed, though he appeared skeptical that management would actually implement suggestions from a line worker. He said he would help however they wanted, but that in his experience, factories rarely changed their procedures based on worker input, preferring to trust engineers and established systems even when those systems were inefficient. McKinley surprised him by saying that the facility's mission was to produce tanks as quickly and efficiently as possible. That pride of authorship had no place in wartime manufacturing, and that if a better method existed, he didn't care whether it came from an engineer or a janitor. He said they would test Walter's approach rigorously, document everything, and if it proved reliable, they would implement it across the entire facility. Over the next 2 weeks, Walter Kowalski became an unlikely consultant to Chrysler Tank Arsenal's engineering department. He worked alongside engineers who had university degrees and years of automotive industry experience, explaining techniques that he had learned through observation and repetition. The engineers, initially skeptical, gradually recognized that Walter possessed a form of knowledge that wasn't captured in their manuals or calculations, a practical wisdom about material behavior that came from thousands of hours of direct experience. They discovered that Walter's method wasn't actually a single technique, but rather a collection of small optimizations, each based on understanding how specific operations interacted. He explained how welding sequence affected plate alignment, how metal grain direction influenced structural strength, how ambient temperature changed optimal torch settings. Dozens of small insights that individually seemed minor, but collectively represented a sophisticated understanding of the manufacturing process. The engineers documented everything, creating modified procedures that incorporated Walter's insights while maintaining quality controls. They identified which aspects could be taught systematically and which required experienced judgment. They designed a training program for experienced workers, testing whether Walter's approach could be transferred to others or whether it was unique to his particular skills. The results exceeded expectations. Of 23 experienced riveters and welders who completed the training program, 19 were able to apply Walter's techniques effectively, achieving similar speed and quality results. The 4 who struggled were workers with less than 6 months of experience, confirming Walter's assessment that the method required a foundation of practical knowledge. By early April, modified procedures had been implemented across 3 production lines, with careful monitoring to ensure quality remained consistent. The impact was immediate and dramatic. Average production time per tank hull dropped from 47 hours to 31 hours, a reduction of 34%. Quality rejection rates actually improved slightly, dropping to 0.9%. But the real revolution wasn't just the speed increase from Walter's specific technique. His success had opened a door that management hadn't realized was closed. Across the facility, other experienced workers began coming forward with their own observations and optimizations. Suggestions that had previously gone unvoiced because line workers assumed management wouldn't listen. A hull assembler named Margaret Chen suggested a modification to the turret mounting sequence that saved 18 minutes per tank. A paint shop worker named James Rodriguez demonstrated a ventilation adjustment that reduced drying time by 40%. A final assembly inspector named Dorothy Williams identified 3 redundant quality checks that could be eliminated without affecting actual defect detection. Each suggestion was small, each represented incremental improvement, but collectively they transformed the facility's output. By June 1943, Chrysler Tank Arsenal was producing 34 tanks per day, an increase of 48% over February production levels. The facility achieved this without additional equipment, without expanding the workforce, and without compromising quality standards. The transformation drew attention from military planners in Washington who had been desperately seeking ways to accelerate armor production. In July, her team of Army Ordnance officers visited the facility to study the improvements and determine whether they could be replicated at other tank manufacturing plants across the country. Walter Kowalski, now officially designated as a production consultant with a modest pay increase, explained his methods to the visiting officers. He described how the breakthrough had come not from sophisticated analysis, but from simply questioning whether an established procedure was actually necessary, from trusting practical experience over theoretical calculation, and from recognizing that sometimes the most complex problems had surprisingly simple solutions. The lead Army officer, a colonel named Robert Patterson, who had spent 2 years overseeing tank production programs, listened to Walter's explanation with evident fascination. When Walter finished, Patterson said this was exactly the kind of innovation the military needed, that too often they became locked into procedures simply because those procedures existed, and that combat readiness required constantly challenging assumptions and seeking improvements. But Patterson also noted something that made the room uncomfortable. He said that in a typical hierarchical manufacturing environment, Walter's innovation would never have happened, that line workers didn't suggest process changes to engineers, and that if Harold Brennan had been a different kind of supervisor, Walter might have been disciplined rather than celebrated. He said the real breakthrough wasn't the technical improvement, but the cultural shift that allowed practical knowledge to be valued alongside engineering expertise. Thomas McKinley, sitting in the meeting, acknowledged this point with surprising candor. He said the facility had learned an important lesson about listening to experienced workers, about recognizing that expertise took many forms, and about creating systems that encouraged rather than suppressed innovation from unexpected sources. He said they had implemented a formal process for workers to submit improvement suggestions, with guaranteed review and feedback from engineering. The program, McKinley explained, had generated over 200 suggestions in its first 2 months, of which 41 had been implemented, and another 73 were under serious evaluation. The cultural impact of Walter's breakthrough had proven more valuable than the specific technical improvement, creating an environment where continuous improvement became everyone's responsibility rather than just management's domain. By the end of 1943, Chrysler Tank Arsenal had produced 8,412 medium tanks, exceeding annual production targets by 19%. The facility received the Army-Navy E Award for Excellence in War Production, a recognition that McKinley insisted should be shared with Walter Kowalski and the hundreds of workers whose practical knowledge had transformed theoretical production capacity into actual output. Walter himself remained characteristically modest about his role. In a brief interview for the plant newsletter, he said he had just been trying to do his job efficiently, that he hadn't set out to revolutionize anything, and that dozens of other workers probably knew similar shortcuts, but had never mentioned them because no one had asked. He said the real credit belonged to management for being willing to listen and to try something different, even when it contradicted established procedures. The broader impact extended far beyond one facility. Other tank manufacturers, aircraft plants and shipyards studied Chrysler's experience and implemented similar programs to capture worker knowledge and encourage practical innovation. The concept of leveraging line worker expertise became formalized in production efficiency programs that helped accelerate American manufacturing output throughout the remainder of the conflict. Industrial historians would later identify this shift as a crucial factor in American production superiority. While other nations relied on top-down engineering expertise, American manufacturing increasingly incorporated bottom-up practical knowledge, creating systems that could adapt and improve continuously rather than following rigid procedures. The combination of engineering sophistication and craft wisdom produced a manufacturing culture that was both disciplined and flexible, capable of rapid innovation without sacrificing quality. For Walter Kowalski, the recognition was simultaneously gratifying and uncomfortable. He appreciated the acknowledgement of his contribution, but disliked the attention and publicity. After the conflict ended, he returned to automotive manufacturing, working at various Detroit plants for another 18 years before retiring. He rarely spoke about his wartime experience, considering it simply part of his job rather than anything extraordinary. But the impact of his stupid shortcut, as he had initially called it when explaining it to Frank Kowalski that night in March, echoed through decades of American manufacturing philosophy. His insight that established procedures weren't always optimal, that experienced workers possessed valuable knowledge that formal systems often overlooked, and that questioning assumptions could lead to dramatic improvements, became foundational principles in post-conflict industrial management theory. The 470 defective armor plates that arrived from Bethlehem Steel in March 1943 had represented a problem that everyone accepted as requiring careful, time-consuming solution. Walter Kowalski's recognition that the problem didn't actually need solving, or at least not in the way everyone assumed, represented a different kind of thinking entirely, the kind that looks past the immediate challenge to question whether the challenge itself is real. By war's end, American factories had produced 88,410 medium tanks, a number that exceeded combined production of all other nations. That overwhelming material superiority came not just from natural resources or industrial capacity, but from countless small innovations like Walter's, from the accumulated wisdom of workers who understood their craft deeply enough to see what textbooks and calculations could not capture. The story of how one factory worker's shortcut built 100 tanks 4 times faster was ultimately a story about the power of practical knowledge, about the importance of listening to experience, and about the revolutionary potential of questioning whether the way things have always been done is truly the only way things can be done. It demonstrated that breakthrough innovations don't always come from laboratories or engineering departments, that sometimes the most sophisticated solution is to simply stop solving the wrong problem. In May 1945, as American tanks rolled through territories across Europe and Asia, few of the soldiers operating those vehicles knew that their equipment existed, partly because a third-shift riveter in Michigan had once decided that a careful procedure designed by educated engineers was solving a problem that didn't actually exist. They didn't know that production had accelerated dramatically because someone had trusted his hands and eyes over calculations and specifications. But the tanks were there in overwhelming numbers, functioning perfectly, a testament to the insight that expertise comes in many forms, and that innovation often requires simply questioning assumptions that everyone else accepts as unchangeable truth. And that concludes our story. If you made it this far, please share your thoughts in the comments. What part of this historical account surprised you most? Don't forget to subscribe for more untold stories from World War II and check out the video on screen for another incredible tale from history. Until next time.